Let us start our discussion on wave mechanics, which is a version of quantum mechanics. So let us consolidate our ideas so far. Associated with every moving particle, there is a matter wave. Okay, de Broglie's idea. And it is represented by a wave function, in general, a complex wave function. And the wave function contains all the information that can be known about the particle. Right. So these are the two features in wave mechanics. First, we need to ask the question how to obtain the wave function for a system. Okay. Then how to extract information from the wave function. Okay. So how do we get the wave function of a system? And once we get the wave function, how do we extract information from the wave function? And these two features together constitute wave mechanics. So we will look at these two features in detail. So let us compare how a system, we consider a single particle as a system, and how this system is analyzed in terms of Newtonian mechanics and quantum mechanics, because we are familiar with what we have done in Newtonian mechanics. So the state of a particle, this single particle constitutes our system. So the state of a particle at time 0, initial time, is specified by giving its initial position at x equal to 0 and velocity at v equal to 0. Okay, instead of velocity at 0, we can also specify momentum at 0. Okay, because momentum is mass into velocity. So these are just two numbers, initial position and initial velocity or initial momentum. So these are, we have just two numbers, x at 0 or v at 0 and v at 0. And what about quantum mechanics? In quantum mechanics, the state of a particle at time 0 is specified by its initial wave function. Let us use the symbol psi for that. Psi at x, 0. I am considering one-dimensional situation here. So psi at the point x and at the time 0. Okay. Now here the difference between Newtonian mechanics and quantum mechanics here is this wave function at the time 0 is an infinite set of numbers corresponding to the value of the wave function at every point x. So this x is a variable. Okay, so we can have different positions at at the initial time 0. The system can have different positions. So at each position, what is a wave function? So we have an infinite set of numbers, the value of the wave function at every point x. So the initial state of a single particle in Newtonian mechanics is just two numbers, is specified in terms of two numbers, x0 and v0, whereas the initial state itself in a quantum mechanical system contains infinite set of numbers. A wave function contains an infinite number of components. Okay, in that sense, a wave function is often called an infinite dimensional vector. So it's a vector with infinite components, because we have to specify the value of the wave function at all x values, which is infinite. Okay. And the next point is in Newtonian mechanics, how the initial state changes with time when the forces acting on the particle are known. So if we know the forces acting on the particle, then we can calculate how the initial state changes with time in Newtonian mechanics, the time evolution of the state. In quantum mechanics, the situation is similar, how the initial state changes with time when the effective potential energy experienced by the particle is known. So in quantum mechanics, instead of dealing with forces, if the particle experiences a force, we express it in terms of the effective potential energy experienced by the particle. So once the potential energy experienced by the particle, effective potential energy experienced by the particle is known, we can calculate how the initial state changes with time. In other words, how the initial wave function changes with time. Now in Newtonian mechanics, this time, the value of position and velocity at a later time can be calculated from Newton's second law of motion. So if we know x0 and v0 at time 0, we can calculate x of t and v of t, position and velocity at a later time, from Newton's second law of motion. Okay. In the same way, if we know the initial wave function, then we can calculate the wave function at a later time, psi at x, t. It can be calculated from Schrodinger equation. So Schrodinger equation in wave mechanics, it plays the role of Newton's second law of motion in Newtonian mechanics. Okay, it gives in Newton's second law of motion gives the time evolution of the state in Newtonian mechanics, whereas Schrodinger equation gives the time evolution of the state in quantum mechanics. So this is the way we can compare Newtonian, the way we analyze a system in Newtonian mechanics and quantum mechanics. Before we go into the details of Schrodinger's theory, let us look at the two approximations in Schrodinger theory. It's not completely general. There is an approximation. There are two approximations there. First is creation and destruction phenomena of particles are ignored. Okay, in any given physical situation, it is assumed that the number of each kind of particle remains constant as the process evolves in time. Okay, so in Schrodinger's theory, the creation and destruction of particles, for example, the absorption of photons, emission and absorption of photons cannot be treated in Schrodinger's theory. So it always assumes that in any physical situation, the number of each kind of particle remains constant as the system evolves in time. Okay. That is one approximation. Now second is, it is assumed that all relevant velocities are sufficiently small so that a non-relativistic approximation is valid. So Schrodinger's theory is a non-relativistic theory. Okay, it's non-relativistic regime, we can say. So these are the two approximations that we use in Schrodinger's theory. Creation and destruction of particles are not considered, and also we assume that the velocities are sufficiently small, so we use non-relativistic calculations. So when we say Schrodinger's theory is an approximate theory, it doesn't mean that it is valid to a limited region. On the other hand, it is applicable to a wide variety of phenomena. So let us briefly look at the range in which Schrodinger's theory can be successfully applied. Even though Schrodinger theory is an approximate theory, it is extremely successful when applied to atoms and molecules. The reason is that in the realm of atoms and molecules, the two approximations in Schrodinger's theory, that is the energies involved are sufficiently small so that the creation and destruction of particles are not involved. Okay, that is one thing. And secondly, the speeds, the velocities of valence electrons in atoms and molecules are non-relativistic. This we have seen when we discussed Bohr atom model. So it is highly successful, extremely successful when applied to atoms and molecules, and particularly in the field of chemistry. Many theoretical expressions for atomic and molecular quantities, such as energies of stationary states, wavelengths of emitted spectral lines, lifetimes of excited states, geometric parameters of molecules, etc., can be expanded in powers of the fine structure constant alpha, whose value is 1 by 137. And in such expansions, Schrodinger theory gives the leading order term correctly, the most predominant term, the first term correctly. We can get that from Schrodinger's theory. We have seen an example of this. For example, when we discussed Bohr atom model, I have expressed many physical quantities. That is the ground state energy of hydrogen atom, the orbital radius, also spectral, the expression for Rydberg formula, okay, Rydberg constant itself. All these things we can express in terms of fine structure constant, okay, which is a dimensionless constant, E square by 4 pi epsilon 0 h cross c, whose value is 1 by 137. In fact, we can do better. We can express these quantities as a power series in alpha, fine structure constant. And when we write this power series in terms of alpha, alpha square, alpha cube, etc., the first term, the leading order term, can be correctly obtained from Schrodinger's theory. And the terms of higher order are relativistic corrections. Remember that Schrodinger theory is a non-relativistic theory. So the higher order terms are relativistic corrections. And these corrections are generally small because of the smallness of alpha. You can see that alpha is nearly 10 raised to minus 2, of the order of 10 raised to minus 2, 1 by 137. So because of the smallness of alpha, alpha square, alpha cube, etc. will be subsequently smaller. So these correction terms are whatever, whether they are relativistic corrections, these terms will be small. And these higher order terms can be calculated using quantum electrodynamics, which is the quantum field theory applicable for atoms and molecules. So the point is that even though Schrodinger's theory is an approximate theory, it's a non-relativistic theory where we do not discuss creation and destruction of particles. Even though these two approximations are involved in Schrodinger's theory, it's highly successful in chemistry, in the realm of atoms and molecules, in atomic physics as well as molecular physics. Also in chemistry, Schrodinger's theory is extremely successful. But the reason is that these two approximations are valid in these systems. And the correction terms, the non-relativistic correction terms and higher order terms, in order to calculate them, we need a more sophisticated theory, quantum electrodynamics, which is one of the quantum field theories. Okay.
Let us consider time-dependent Schrodinger equation, which is the fundamental equation in non-relativistic quantum mechanics. Let us consider a free particle, or in general a particle of mass m moving along the x direction, and this particle experiences some force field, and this force field can be represented by an effective potential, let us say V, which depends, in general it depends on position as well as time. Okay, this is an effective potential experienced by the particle. Then the matter wave function, so the matter wave function of this particle is, let us say, psi, which depends on position and time. So this particle has wave nature as well as particle nature, and the matter wave function is, suppose it is represented by some unknown function psi. Then this matter wave function satisfies the equation, the differential equation given by IH cross, where H cross is Planck's constant divided by 2 pi, H by 2 pi. IH cross dou by dou T of psi equals minus H cross square by 2m dou square by dou x square psi plus V psi. This is the differential equation. We can also call it wave equation, satisfied by the wave function, the matter wave function of this particle moving in a force field represented by an effective potential V. And this equation is called time-dependent Schrodinger equation in one dimension. In one dimension because particle is moving along the x-axis. Okay, so that its wave function depends only along the x-coordinate. So this is time-dependent Schrodinger equation in one dimension. This was discovered by Erwin Schrodinger in 1926, in the beginning of 1926. His 4 papers on quantum mechanics came in 1926. And what about motion in 3 dimension? If the motion is along 3 dimension, the wave function will depend upon x, y, z and t. If you are using Cartesian coordinates, it will depend upon 3 coordinates. Then the change is that in general, the potential energy also will depend upon x, y, z and t. Then the change is that here we have a second order derivative in x. So we will have another term dou square by dou y square psi plus dou square by dou z square psi. And you have studied in your electrodynamics that dou square by dou x square psi plus dou square by dou y square psi plus dou square by dou z square psi. It can be expressed in a compact form by introducing the Laplacian operator del square. Okay, so the 3-dimensional Schrodinger equation in 3 dimensions will be like this. So let me write position vector r t. Okay, as a compact way of saying that vector r means ix plus xi plus yj plus zk. So the position, either we can say the wave function depends on x, y, z and t, or we can say it depends upon vector r and t. It involves the three coordinates equals, and dou square by dou x square psi plus dou square by dou y square psi plus dou square by dou z square psi, together we can write in a compact form del square psi. Okay, and this potential energy also depends on the three coordinates. Okay, so there is a physics point of view, there is no change here. Only thing is that instead of one coordinate, there are now three coordinates. Okay, both in wave function as well as potential energy. This is time dependent Schrodinger equation in three dimension. And suppose we are talking about a free particle. Okay, then there is no force field. Then the potential energy, effective potential energy is 0. So what is a free particle Schrodinger equation? Let us consider only one dimension now. So for free particle Schrodinger equation in one dimension, we can just put potential energy equal to 0. So what you get is okay. So this is a free particle equation in one dimension. Free particle Schrodinger equation in one dimension. And what we have to clearly understand is that this is a fundamental equation in non-relativistic quantum mechanics, in the sense that Newton's second law of motion is the fundamental equation in classical mechanics. This equation cannot be derived from more fundamental principles. Okay, this is the starting point, this is the fundamental equation. So Schrodinger equation cannot be derived, okay, in the sense that Newton's second law of motion you cannot derive. That is the starting, that is a fundamental equation. Okay, so now what we are going to do is, let us consider this free particle Schrodinger equation, and we will see, or we want to see what type of solution does this equation have. What can be the solution of this equation? Now we are talking about a free particle. There is no, consider a free particle like this. There is no potential energy. A free particle is moving along the x-axis. For the convenience of minimizing the number of coordinates, we will look at only one-dimensional motion. Okay. Whenever we want a three-dimensional situation, we will generalize into three coordinates. The essential physics is the same. So consider a free particle moving along the x-axis. If it is a free particle, okay, there is no force acting on the particle, then we know from classical mechanics that if there is no force, effective force acting on the free particle, then it will be in uniform motion. Okay, that means its velocity will remain constant. Or another way of saying is that its momentum will remain constant. So a free particle has constant momentum. Now when we try to think about its matter wave function, okay, or matter wave packet, then what can be the wave function or wave packet of a free particle? If it's it's a free particle, its momentum is constant, then it has a exact momentum p, right? If it has an exact momentum, then its wave nature should be such that the wavelength should be exact. It should be having an exact wavelength lambda. Why? Because there is a relationship between momentum of the free particle and its matter wavelength. That is de Broglie's equation, lambda is equal to h by p. Okay. So if the free particle has a constant, if it is a free particle, it has a constant momentum. That means it has as a constant wavelength lambda. Then one way of thinking about it is, if we consider the ideal case, if it has an exact momentum and an exact wavelength, then it should be represented by a plane wave of infinite extension. Okay, why infinite extension? In order to get exact infinite accuracy or exact value of lambda, it should have an infinite extension. Okay, if it has a finite extension, then there will always be an uncertainty, an error in lambda measurement, and hence an error in momentum measurement. This we have discussed in detail when in our discussion on uncertainty relationship. Okay, if you take a wave of any finite extension, then there is always invariably there is some error in the wavelength measurement, then there will be an error in the momentum measurement. So if we think about an ideal free particle of exact momentum, then its wavelength should be exact, then its extension should be infinite. So consider the wave function of such a free particle, or the matter wave of such a free particle is a wave of infinite extent. Okay. Then does it satisfy uncertainty relationship? Yes, in the extreme way. That is, if momentum is exact, P is exact, it means that uncertainty in momentum is 0. Okay. Now, if uncertainty in momentum is 0, then uncertainty in position should tend to infinity. What does it mean? It means that its position cannot be determined. If we are talking about a free particle moving along the x-axis, its position can be anywhere between minus infinity and plus infinity. Right. Then uncertainty relationship between position and momentum still holds in the extreme sense, in the limiting sense. That is, momentum is exact and uncertainty in momentum is 0. Position is completely unknown. Okay, uncertainty in momentum is infinitely large. And this means that the matter wave of the free particle should be of infinite extension. Okay, so there is no problem with the uncertainty relation. It's a limiting case. So what we are going to do is, let us consider such a wave function for a free particle, and let us see if it satisfies this free particle Schrodinger equation. Okay, so let us see that. Now, in the case of a system in quantum mechanics, the wave function can in general be complex. It can be real also, but in general it can be complex. So we start with a complex wave function. So we are going to use a plane wave function. So in the one-dimensional case, so let us start with some constant a, exponential I, okay, what is e raised to I kx minus omega t? It's a combination of cos kx minus omega t plus I sin kx minus omega t. So it's complex. There are two parts, a cosine part and a sine part. And we know that this cos kx minus omega t or sin kx minus omega t is the form of a wave traveling along the plane wave traveling along the positive x direction. So we are considering a free particle moving along the positive x direction. Equivalently, we are using a plane wave traveling along the positive x direction. Okay, we have in one of our previous classes we have discussed how this wave function comes for a plane wave traveling along the positive x direction. So we are using a complex wave function for a matter wave. Okay, so in the case, this is for any wave for traveling along the positive x direction, any plane wave traveling along the positive x direction. Now, if it is a matter wave, we can connect the wave number with momentum with using de Broglie's relation. We know P is equal to h cross k. Okay, this comes from de Broglie's equation. P is equal to h by lambda. Just multiply numerator and denominator with the 2 pi. So we get h by 2 pi into 2 pi by lambda. H by 2 pi is h cross. 2 pi by lambda is k. Then we can write k is equal to p by h cross from this. And also angular frequency omega we can connect with the energy of the particle. The equation is E equals h cross omega. Where does it come from? From Einstein-Planck equation. E equal to h nu. Just multiply again numerator and denominator with 2 pi. We get h by 2 pi into 2 pi nu. H by 2 pi is h cross, 2 pi nu is omega. So let us write omega as E by h cross. So let us substitute. This is, I understand that this equation is applicable for any plane wave traveling along the positive x direction. But what we are going to do now, we are going to write down now, is applicable only for a matter wave traveling. So this is a e raised to I. Instead of k, I am writing p by h cross. Okay. Instead of omega, I am writing e by h cross. So h cross is common. I will take out. So I by h cross into px minus et. Okay. So this is a matter wave function of a free particle traveling along the positive x-axis. Okay. So let us call it equation 1. Now I am going to differentiate this equation with respect to time. So first derivative in time is equal to. So what happens when we differentiate with respect to time? This constant a will be there, and exponential of something, if you differentiate, you will get the same function. So we get e raised to I by h cross px minus et. Then if you use function of a function rule, there is the time dependent part is this, so its coefficient will come out. Okay, what is the coefficient of the time dependent part? Minus e, and there is I by h cross also, so I by h cross into minus e will come out. So what you get is minus I by h cross into e. Okay, the remaining term is a e raised to I by h cross px minus et. So I can put a psi for that. Okay, you try this differentiation. Then I slightly rearrange this. What I am going to do is, let us multiply both sides with IH cross. So IH cross dou psi by dou t is equal to, what happens when you multiply this side with IH cross? H cross will cancel. I into I becomes I square, and what is I after all? I is square root of minus 1 is I. So I square is minus 1, minus and minus will be plus. So we have E psi. Call it equation 2. Okay, maybe I will write this relation here. IH cross dou psi by dou t equal to E psi. Okay. Again, let us come back to equation 1. This time I am going to differentiate with respect to x. So dou by dou x of psi. What happens? You are differentiating with one of the variables. So exponential of something you are differentiating, then you will get the same value. You get a e raised to I by h cross px minus et, and then you differentiate with respect, you are differentiating with respect to x. So the coefficient of x will come out. Coefficient of x is I by h cross into p. This e and p are constants for a free particle. Its energy is constant, its momentum is also constant. So I by h cross into p will come out. So what you get is I by h cross into p. The remaining term is this, which I am going to put as psi. Okay. Yes. I am going to differentiate once more, because remember that in our Schrodinger equation you have dou square by dou x square psi. So let us differentiate once more. So what is this dou square by dou x square psi? Again, as for in order to differentiate that, we have to put back this psi. Psi is again, remember, a e raised to I by h cross px minus et. So this part is constant, so we are going to differentiate this part. Again, you will get a e raised to I by h cross px minus et. And then once more you have to put this, you have to take this coefficient of x come out. So you get, already you have an I by h cross into p here. When you differentiate once more, one more I by h cross into p will come out, and once more you will get psi. Okay. You are this part is a constant, so you are differentiating this psi with once more. So this is I by h cross into p, dou psi by dou x. What is dou psi by dou x? This is. So you can substitute that here. So what you get here is, what is this? I into I is, I square is minus 1. So we have p square by h cross square with a minus sign psi. What I am doing is, I am multiplying both sides with minus h cross square by 2m. So minus h cross square by 2m dou square by dou x square psi is So you have not multiplied left side with minus h cross square by 2m. So right side also you have to multiply. So h cross square will cancel, minus sign will cancel, and there is a 2m in the denominator. So you have p square by 2m into psi. That is called equation 3. And I am writing it here. Minus h cross square by 2m dou square by dou x square psi is equal to p square by 2m psi. What is the energy of the free particle? There is no potential energy since it's a free particle. There is no force field, so there is no potential energy. So its only energy is kinetic energy. So the energy of a free particle we can write as its rest energy plus kinetic energy. Right? Rest energy plus kinetic energy. Suppose this rest energy is a constant. Okay, so what we can do is we can just rearrange or refix the energy scale such that the energy scale starts from the rest energy. Or in other words, we can just assume that its rest energy is 0. I am not considering that its rest mass is 0. It's a particle of rest mass m. Okay. But I am just rescaling the energy scale, that's all. Okay. It's just like saying that when you measure your height, okay, what is the height? How do we measure the height? It's a height difference between the head, the position of the head, and the position of the toe, right? Then what we are assuming when we use a scale, what we assume is that the position of the toe is the height at the position of the toe is 0, and height at the head is something. So what is the height difference? This minus 0. That's all. But here what we are doing is the ground on which we stand, we assume that its height is 0. But it not necessarily be so. We are using a scale that starts with the ground on which you stand has 0. But that doesn't have to be so. One can start from, let us say, sea level. Or you may be on a high-story building. Then you can start with the ground floor of the building. Then the height of your toe need not be 0 when you start with the ground floor. But then the height of your head, you have to again start with the ground floor. But when you take the difference, it will be the same. So you can start with the sea level, then the height of your toe will be something else. Okay, so whenever we measure height, we are actually measuring height difference between the head and the toe. And for that we are using a scale which starts with 0 as the height of the toe. In the same way, in this energy scale, we just conveniently use, and since this is a constant value, we conveniently shift the energy scale and we say that energy scale starts with the rest energy. So the 0 on the energy scale starts with the rest energy. If that is so, we can say the energy of the particle you can write as total energy of the particle we can write as simply kinetic energy. Okay, so please keep in mind that it doesn't mean that its rest energy is 0. We are just rescaling the energy scale. Okay, so let us just multiply both sides with the wave function psi. Okay. Now look at these two equations. In the equation 2 and 3 that we have obtained earlier. This E psi we can write in terms of the wave function, some derivative, time derivative of the wave function like this. So instead of E psi, let me substitute this I h cross dou psi by dou t. And this p square by 2m psi, okay, instead of that we can use another second order position derivative of wave function. So we have minus h cross square by 2m dou square psi by dou x square. Look at this. This is nothing but call it equation 4. This is nothing but free particle Schrodinger equation in one dimension that we have written down earlier. Okay. So what we have shown is that if we start with a wave function of this form, okay, if we start with a complex plane wave function, then it is the solution of, it satisfies free particle Schrodinger equation, or this is the solution of free particle Schrodinger equation. That is what we have shown now. What about a general Schrodinger equation involving an effective potential? One point that we can notice is that Schrodinger equation is a linear differential equation, and it's also a homogeneous differential equation. Okay, we will discuss the properties of Schrodinger equation in some more detail later. For the time being, notice that it's a linear differential equation, because linear means in each term the power of psi or its derivative is 1. Okay, here dou psi by dou t has the power 1. Second derivative is there, dou square by dou x square of psi, but the power of this term is 1. Okay, there is no square term or cubic term. That is why we say that it's a linear differential equation, and it's also a homogeneous differential equation, because all the terms contain the unknown function psi. There is or its derivative. There is the first derivative here, there is a second derivative here. Every term contains, even if you look at the general Schrodinger equation, one more term is there, some potential energy into psi. So every term contains either the wave function psi or its derivative. So it's a homogeneous differential equation. There is no constant term without psi. So it's a linear and homogeneous differential equation. If a differential equation is both homogeneous and linear, then if we have two solutions, let us say psi 1 and psi 2 are two solutions of this equation, then any linear combination of these two solutions, C1 and C2 are constants, so it can be any constant plus or minus. So any sort of linear combination of these two solutions will also be a solution of a linear homogeneous differential equation. What does it mean? It means that if psi 1 and psi 2 are two plane wave solutions of Schrodinger equation, then a linear combination of these plane wave solutions will also be a solution of the Schrodinger equation. And the number need not be 2, you can consider any number of plane wave solutions. Then the linear combination of all these plane wave solutions will also be a solution of the Schrodinger equation. And we know that when we take linear combinations of plane wave functions, we essentially will get is a matter wave packet of whose matter wave will be a wave of finite extension. Okay, so it means that by taking proper linear combinations of plane wave solutions of Schrodinger equation, we can arrive at a wave packet solution of Schrodinger equation, which is of a finite extension. So it means that a wave packet, which is expressed as a Fourier integral in this form, some integral, this is some amplitude, it's the amplitude of the plane wave. Then we can use plane waves of this form, a raised to some instead of a I am writing an amplitude which depends on k, so I by h cross okay, and in this case this E may vary with k. E need not be constant, it may vary with k. So this type of matter wave packet, this is a Fourier integral which represents a matter wave packet. This can be the solution of general Schrodinger equation involving a potential energy function. So that is the idea. Since Schrodinger equation is a linear and homogeneous differential equation, from the plane wave solutions, it's we can construct solutions which are wave packet solutions of Schrodinger equation. So the solution of a general Schrodinger equation will be a wave packet. It can be expressed as a Fourier integral of this type of a form. Okay. So we have introduced the time-dependent Schrodinger equation, which is the fundamental equation in non-relativistic quantum mechanics. We have also shown that a plane wave function, which is the wave function for a free particle, can be the solution of the Schrodinger equation. Okay. When we say that matter wave function is complex, it doesn't mean that it's imaginary. That is, a part of it is imaginary, not real. It doesn't mean like that. A complex function is simply a combination of two real functions. When we write matter wave function as e raised to I kx minus omega t, it's a combination of two real functions, cos kx minus omega t and sin kx minus omega t. Okay. So in many cases, there are cases where matter wave function can be real, but there are cases where in general it is complex. So in many situations we cannot express matter wave function using a single real function. We need two real functions. Okay, then we can ask the question, why don't we write Schrodinger equation in terms of real functions? Okay, then the answer is that if we use two real functions instead of a single complex function for matter wave, we will get two Schrodinger equations. We will just see that using free particle Schrodinger equation. Now suppose we write our wave function. Let us use one-dimensional situation. Suppose we write this as some psi 1 xt plus psi 2 xt plus I times psi 2 xt. After all, our choice e raised to I kx minus omega t means cos kx minus omega t plus I times sin kx minus omega t. So instead of this complex function, what happens when we use two? What happens when we write this as combination of two real functions? Then let us write down the equation in terms of psi 1 and psi 2 instead of psi. Then what does it? How does it look like? We know that the free particle Schrodinger equation is IH cross dou by dou t of psi is minus h cross square by 2m dou square by dou x square of psi. This is the free particle Schrodinger equation. Suppose instead of psi, if we substitute this psi 1 plus I psi 2 here also. Okay. Then what are the equations of psi 1 and psi 2, these real functions? We can equate, so there are real terms on both sides, there are imaginary terms on both sides. So let us equate real parts and imaginary parts. What is the real part on the left hand side? This IH cross dou by dou t of psi 1 is an imaginary part. But second part, IH cross dou by dou t acting on I psi 2. I into I will be I square minus 1. So we have minus h cross dou by dou t of psi 2. This is the real part on the left hand side. What is the real part on the right hand side? Minus h cross square by 2m dou square by dou x square of psi 1. There is no I here. So minus h cross square by 2m dou square by dou x square psi 1. We have equated the real parts on both sides. We can cancel this minus sign. So this is one equation. H cross dou by dou t psi 2 equals h cross square by 2m dou square by dou x square psi 1. Similarly, if we equate the imaginary parts on both sides, this is the imaginary part. IH cross dou by dou t psi 1. We don't need this I. We take the imaginary part only. Similarly, there is a term involving I here, minus h cross square by 2m dou square by dou x square I psi 2. Okay, we can remove the I from there also. So minus h cross square by 2m dou square by dou x square psi 2. When we equate the imaginary terms on both sides, we get this. H cross dou by dou t psi 1 is minus h cross square by 2m dou square by dou x square psi 2. So these two equations represent this is equivalent to the free particle Schrodinger equation. The difference is that now we have written down the equations in terms of only the real functions. Only the real parts, real functions involved inside this complex function, combined in this complex function. But what is the advantage here? Instead of a single Schrodinger equation, we have now two Schrodinger equations. That is fine, but there is any advantage of writing this in this way only if we are able to measure the psi1 and psi2 separately. Okay. But in the case of any system, we cannot measure the wave function directly. We cannot measure psi1 and psi2 directly, experimentally. We cannot measure it. What we measure experimentally is the probability density of the particle, probability density of the system. What is the probability density? Probability density is simply psi star psi, or we can use this notation mod psi square. So what we measure is only mod psi square, probability density. We cannot measure psi. So if we cannot measure the wave function, then we cannot measure, it means we cannot measure these real functions psi1 and psi2. We cannot measure psi, which means we cannot measure psi1 and psi2. If we cannot separately measure psi1 and psi2, then there is no point in writing two equations separately. The economic way of writing is we can combine these two real functions into a single complex function, and instead of dealing with two separate Schrodinger equations in terms of real variables, we can use a single Schrodinger equation in terms of a complex function. So treating the matter wave function as a complex function is for convenience. Instead of two equations, we can use a single equation. So what we have to keep in mind is that the matter wave function involves two real functions. Okay, and since these two real parts cannot be measured, what we are using, we are using them as a combination. We are using a single complex function. That is the idea. And this is comparable to the situation in electrodynamics. In electrodynamics, we have, in the case of an electromagnetic wave, we have an electric field and a magnetic field. The wave function of electromagnetic wave contains two wave functions, actually, two vector functions, an electric field as well as a magnetic field. Okay, so there are two real parts there. What is the wave equation of electromagnetic wave? We write the wave equation for electric field as well as magnetic field. If it's a three-dimensional equation, del square E equals 1 by c square dou square E by dou t square. This is the wave equation for the electric field, and similarly wave equation for the magnetic field is right, where electric field and magnetic field are two real functions. So we can see in the same way here. So we have to when we write the Schrodinger equation in terms of two real functions. These equations are equivalent to, here I have used three dimensions, but in one dimension you have dou square E by dou x square or dou square B by dou x square. So these two equations are equivalent to these two equations. Okay, but the difference is that in the electromagnetic wave we write the equation of electric field and magnetic field separately. We treat electric field and magnetic field separately, these two real functions separately, because they can be measured. Electric field and magnetic field, they can be measured, they can be experimentally measured, they have separate identities. Okay, so that is why we are treating them as separate. It's possible to combine these two together in terms of a single complex function. Okay, but we don't do that in electromagnetic wave because this electric field and magnetic field can be experimentally measured and they have separate identities. But here in the case of matter wave, we don't do that. For the wave equation of matter wave, we don't do that. We don't write two wave equations for the two real parts, but because they cannot be measured. They don't have separate identities. They cannot be measured. So that is why we combine them into a single complex function. Okay. Let us briefly consider properties of Schrodinger equation. We will discuss three main properties. The first one is it is first order in time. Now, in this sense, Schrodinger equation is different from other wave equations. Okay, this is our Schrodinger equation. Let us consider one-dimensional case. Okay. It is first order. The time derivative is first order, first derivative. Space derivative is, position derivative is second order. Let us look at other wave equations. For example, waves on a stretched string. So we have an equation like this. Let us write the time derivative here. Okay. Here y is the transverse displacement of the string. So you can see that there is a second derivative in time and second derivative in position. Okay. And similarly, electromagnetic waves. So it has both electric field and magnetic field components. We have v is the velocity of the wave on the string. Here instead of v we have c, speed of light in vacuum. So in vacuum it looks like okay, it's an electric field vector, but it varies only with the wave is moving along the x direction. Okay, and similarly you have a magnetic field component. So in the case of wave on a stretched string, electromagnetic waves, you have a second order time derivative, okay, and second order position derivative, whereas in the case of matter wave equation in non-relativistic regime, that is in Schrodinger equation, we have first derivative in time. So that is a unique property. It's first order in time. And second property is it is homogeneous. What does it mean to be homogeneous? It means that in Schrodinger equation, all the terms contain either the wave function, the unknown wave function psi, or its derivative. Okay, so you have the first derivative in time here, dou psi by dou t. You have second derivative in position here, the wave function here. So every term contains at least either the wave function or its derivative. There is no term independent of psi. That is what meant by homogeneous. Let us look at the other wave equations. These are also homogeneous. Okay, all the terms contain the derivative of y. All the terms contain derivative of electric field or magnetic field. So these are also homogeneous. Okay. So that is the meaning of homogeneous. And what is the consequence of that? The consequence is that if psi is a solution, okay, suppose psi is the solution of Schrodinger equation, then a constant times psi is also a solution. If you multiply psi with any constant, you will get the same solution. Just look at here and see if psi satisfies the Schrodinger equation. Just multiply a constant here. Then you can see that a times psi is also a solution of Schrodinger equation. On the other hand, suppose we had a term like this, let's say some f of x, which does not contain psi. Then what happens is, if we multiply throughout with a, then there is a term here. So now this equation is different from the previous equation. In the previous equation, this constant term contains only f of x. Now it contains, this is the actual equation. Now it contains f of x times a, an extra constant. So the equation has become different. So since there is no such source term or non-homogeneous term in Schrodinger equation, any solution multiplied by a constant is also a solution. We will later see that this has importance when we discuss the normalization of the wave function. Okay. So other wave equations are also homogeneous. Now third property is that it is a linear equation. What is the meaning of linear equation? If we look at each term, okay, if we look at each term in the Schrodinger equation, let us look at the power of each term in the Schrodinger equation. The power, okay, here psi, the power is 1. Dou square psi by dou x square, power is 1. Dou psi by dou t, power is 1. Okay, there is first derivative here, there is second derivative here, okay, but the power of the first derivative, okay, this is 1, this is 1, this is 1. There is no square term or cubic term, okay, higher powers are not there. Such an equation is linear equation. Again, we can see that these are also linear equations, okay. If there is a power different from 1, we get a non-linear equation. Okay, in physics, there is a non-linear physics, non-linear dynamics is there, but there are a large class of equations in physics which are linear equations. Schrodinger equation is also a linear equation. Now, what is the consequence that if there is a linear equation? If psi 1 and psi 2 are two solutions, okay, then psi 1 plus or minus psi 2 is also a solution. That is the idea of a linear equation. You can easily check that, write the Schrodinger equation for psi 1, write the Schrodinger equation of psi 2, just add them, add the two equations. You will get, you can show that psi 1 plus psi 2 is a solution of Schrodinger equation, or psi 1 minus psi 2 is a solution of Schrodinger equation. Now, this second property and third property can be combined, okay. So, if it is linear and homogeneous, we can say that these two properties can be combined, and we can say that if psi 1 and psi 2 are two solutions, then you take any linear combination of psi 1 and psi 2, C1 psi 1 plus C2 psi 2, where C1 and C2 are two constants, is also a solution. This can be easily proved. Okay, write the Schrodinger equation for psi 1, write the Schrodinger equation of psi 2, multiply first equation with C1, second equation with C2, add the two equations. And you can take the common derivatives outside. You can show that, you can write the Schrodinger equation for some psi which is equal to C1 psi 1 plus C2 psi 2. So this is also a solution. What is the importance of this one? Suppose psi 1, psi 2, etc. So you can add the number. Psi 1, psi 2, psi 3, psi 4, etc. So if you have a set of solutions of Schrodinger equation or such linear homogeneous differential equations, then linear combinations of these solutions is also a solution. It means that if psi 1, psi 2, psi 3, etc. are plane wave solutions, we know that a plane wave can be the solution of free particle Schrodinger equation. We have shown that. So if we have a set of plane wave solutions, then their linear combinations can also be a solution of the Schrodinger equation. But the linear combination of a set of plane wave solutions, plane wave equations, can become the wave function for a wave of finite extension, a wave packet. Okay, so this shows that we can construct wave packet type solutions out of linear combinations of plane wave solutions. So a wave packet can also be a solution of Schrodinger equation. So in the case of a plane wave is representing a free particle. This we have discussed before. A plane wave represents a free particle having constant momentum. But the plane wave has infinite extension. Its momentum is exactly known, but its position is completely uncertain. We don't know where its position is. Its localization is not possible. But if we want to confine the particle to a particular region, then we need a wave packet of finite extension. So when we confine the particle to a particular region, it experiences, in general, it experiences an effective potential. So when we write the Schrodinger equation for a particle experiencing an effective potential, okay, then what the solution should be? A wave packet of finite extension. So is it possible? Yes, it is possible. From the plane wave solutions, we can construct wave packet type solutions of Schrodinger equation. Okay, this comes from the these two properties because it's linear and homogeneous. So we can conclude that the Schrodinger equation is a second order partial differential equation. Second order because the highest derivative is 2, second order in space coordinates. So it's a second order partial differential equation, or it's a second order linear homogeneous partial differential equation. Okay. So these are the major properties of Schrodinger equation.
Let us summarize the algorithm of Schrodinger's theory, or algorithm of wave mechanics. We have seen that the two features, the first feature in wave mechanics is the question how to obtain the wave function for a system. Okay, now this is the algorithm for that. Get the potential energy of the system first. Then solve the Schrodinger equation of the system. Write down the Schrodinger equation. We know that it's a second order partial differential equation which is linear and homogeneous, and solve this Schrodinger equation of the system. The solution gives the wave function of the system. The solution of the Schrodinger equation gives the wave function of the system. So this is how we obtain the wave function of a system. So the next question is how to extract information from the system. So in the next class we will look at that question, how to extract information from the system.